So in this lesson, we're going to talk about polygons. Polygons just mean many sides, so a many-sided shape. So anything you could probably think of is a polygon. So a triangle, that's a polygon because it has 3 sides, just as a square and a rectangle both have 4 sides, so those are polygons. Now, instances of what we don't qualify as polygons are circles or ellipses or semicircles. So while technically maybe they have many sides, we don't really treat them the same way. They don't necessarily follow the same rules. Whoops. So we want to talk about just polygons. So many sides, many straight sides. And so regular polygons, what these are going to be, regular just means the same measure. So for polygons, we're going to say that regular polygons have equal sides. So if I have a regular polygon that's 4 sides, that's a square. So we can see 1, 2, 3, 4. This is 4 equal sides, and that's a square. And these little tick marks, these mean that they're the same measure. So sometimes you might see a shape like this, which is a rectangle, and we'll say that these 2 sides are equal, but these 2 are also equal, but to each other, not the other sides. So these single tick marks mean these are equal. These double tick marks mean that these opposite sides are equal, even though these 2 sides are not equal to one another. Right, and I could also, I did that again, I could also have a regular triangle. So a regular triangle, which that is not a regular triangle. There we go. Best I can. Something like this, where these sides are equal. This is 3 equal sides, and you may know this as an equilateral triangle. Don't worry about the name. We'll work more with equilateral. We'll work more with triangles coming up, but just know that this is 3 equal sides, and these are both regular polygons. Now we do also have this idea of convex versus concave. You may have seen convex and concave mirrors, and so whenever you see convex, that means it's going outward. So let's say I have a shape just like this. So 6-sided polygon. If I look at these sides and I extend them out, just like this, notice that as I extend these lines, there are no intersection points inside the polygon. So if there are no intersection points, inside, that means it is a convex polygon. Much in the same way a convex mirror pops out. Now if I have, let's see, can't really see some good examples. Maybe this. This is a little bit different, it's a little house or arrow. If I want to find out if this is convex or not, again, I can extend these sides. So there looks good, but then as soon as I extend these, you can see that these lines cross through the inside. So because this inside is full and I have intersection points inside, that means that this is going to be a concave polygon. I wish there were a quick and easy way to describe these and to remember these, but you're just going to have to remember the definition. and apply them to polygons in the future. So again, convex kind of pops out, and there are intersection points inside. There are no intersection points inside. And concave sort of angles inward, and we can have intersection points inside. So that is going to be concave. Then we have this idea of perimeter. Perimeter is just the total distance of the sides. And you may have seen this before. So if I have this rectangle, and I say that this is 3, this is 3, maybe that's 5, not drawn to scale. Actually, maybe I can make that a little bit more accurately. Maybe this is going to be something like 8. So if I have this perimeter of this rectangle, perimeter is going to equal the 2 sides plus the 2 sides, so the 4 sides added together. So this is going to be 6 plus 16, which is going to give me 22. Now it is important to note, and you may have had teachers like this in the past, if we have a unit, we need to include that as well. So the full answer, if these are measured in centimeters, would be the perimeter is 22 centimeters. And here are some examples. Now it's important to see that for this rectangle, we only label 2 sides. That does not mean that these are the only 2 sides. We can clearly see that there are sides here. With a rectangle, we know that opposite sides are congruent. So we're going to say that this is 17 and this is 4. So the perimeter for 4 is going to be 2 times 4 plus 2 times 17. So perimeter is going to be 8 plus 34, and that's going to equal 40. Oops, not 44, 42. 42 feet. So perimeter there is 42 feet. I'll hold off on the circle for just a bit. For number 6 here, this 7 millimeters, you don't really need to worry about that. We're not finding the, don't find the area. We're not finding the area of this. What we're doing is we're finding the outside. So if this, we can see this tick mark there, so that means that this is 8.1. So what we have for the perimeter is we have 2 times 8.1 plus 8. So the perimeter is going to be 16.2 plus 8. So we're going to have that the perimeter is going to equal 24.2 millimeters. It's a sad looking M. 24.2 millimeters. Now circles, we didn't really discuss this. You may remember this. We actually called the perimeter circumference. It still means the distance around, but because technically this isn't one side, we're going to say this is the perimeter, and the formula for this is 2 pi r. R is the radius. So this 7 here, that is r. So the perimeter is going to be 2 times pi times the radius, which is 7. So we're going to get that this is 14 pi miles. I'm going to leave the pi in there, and that's okay. Most of the time when we're dealing with circles, it's going to be okay for us to leave a pi there and not multiply out and get a decimal. Circumference isn't too important, and later on in the year we will look at circles more clearly, and we'll also look at area. So for these questions, don't worry about area now. We're just looking at perimeter. Okay, now we could also have some coordinate geometry where we need to look at these points and we need to find the perimeter. Well, perimeter is the distance around. So if I think about these points and what they look like, so for number 7 here, just draw a quick sketch. So I have 1, 2, 3, 1, 2. That's going to be O. And then I have 1, 2, and that's P. And then I have 1, 1, 2, 3, 4, and that's going to be Q. Then I have R, which is 3, negative 4. It's a nice little rectangle there. So what's the distance between P and O? Well, because they have the same y-coordinate, we can see it's just this horizontal line. So the distance for this side to go from 1 to 3, that's going to be 2. So because it's a rectangle, we can see that down here from Q to R, that's also going to be a distance of 2. The y-coordinates are the same. The only thing is the difference in the axes, and that distance is 2. The distance from O to R, so this long distance here, the x-coordinates are the same. Notice we have x's as 3's. So what's the difference in the y's? Well, the difference in the y's is that we have 2 to negative 4. So 2 minus a negative 4, that's 6. If we count here, that's going to be 6 spaces. And if we do the same, PQ is also going to be 6. So the perimeter here, is going to equal 2 times 2 plus 2 times 6, which this is going to give us 4 plus 12, which is 16. For number 8, we can see we have 3 points, so that's going to give us a triangle. So if I just do a quick little crude draft, 0, 0, that's going to be S. T is going to be 1, 2, 3, 1, 2. And then U is going to be 8. So 1, 2, 3, 4, 5, 6, 7, 8. We want to find the perimeter. Now, unfortunately, we can count this up from S to U. That's going to be a distance of 8. However, if I think about these other sides here, these are not lines that I can just count across. So what I'm going to need to do is the distance formula. Yes, the distance formula is back, and we're going to use it. So the distance for, let's find ST, is going to be the square root of, remember this is going to be the change in the x's squared plus the change in the y's squared. Actually, let me change that formula so we have those subscripts as 2's, because I know that's the one that I did use before. It doesn't really matter which x values we which subscripts we use. All right, so if I'm looking from S to T, S is 0, 0. So that's perfect. So I'm going to have 3 minus 0 squared plus negative 2 minus 0 squared. So this gives me the square root of 3 squared, which is 9, plus the square root of negative 2 squared, which is 4. So that means that ST is equal to the square root of 13. Perfect. For the second side here, UT, we're going to have, again, the distance formula. So this is going to be x's, so 8 minus 3 squared, plus 0 minus the negative 2 squared. So this is 5 squared, which is 25. 0 plus 2 is 2, times itself is 4. So we get that UT is equal to the square root of 29. So the perimeter would be 8 plus the square root of 13 plus the square root of 29. Now, because we cannot combine these in any way, we could leave our answer like this. Now, if we did want to, we could also get a decimal approximation And so if we do that, we could just type this into our calculators. And so we can find that the perimeter is about equal to 16.99. So sometimes we're going to use the distance formula. Other times we can just count. But remember, if you're not sharp with the distance formula, definitely go back and review that. All right, here's a good word problem, a good challenge question. So it says that a landscape designer is putting black plastic edging around a rectangular flower garden that has a length of 5.7 meters and width of 3.7 meters. So we can see that's exactly what we have here. Now the edging is solid. Hopefully it's solid. It's sold in 5-meter lengths. So we want to find the perimeter of the garden and determine how much edging the designer should be. Now this part right here, this means we're going to need to round up for our answer. So we just want to edge this around. So we're putting this plastic edging around this dimension. So the perimeter is going to be 2 times 5.7 plus 2 times 3.8. So this right here is going to be 11.4, and this is going to be a 7.6. And we add these together, and we're going to get 19. And this is 19 meters. So that's the perimeter, is 19 meters. However, the edging is only sold in 5-meter lengths. So if I divide 5 into 19, we can see right here, if I want to have 19 meters worth, I'm going to need 3 4/5 pieces of wood. But we can only buy them equally. So I'm going to round this up. So that means that I need 4 pieces. So I need to round up, which is going to bring my total to 20 meters. Now for the second part, suppose that the length and the width of the garden are tripled. What is the effect on the perimeter, and how much edging should the designer buy? Well, let's figure that out. So if I triple the length and the width, 5.7 times 3, that's going to be 17.1, and 3.8 times 3 is going to be 11.4. So now the new perimeter is going to be 2 times 17.1 plus 2 times 11.4. So this is going to be 34.2, and this is going to be 22.8. So if I add these together, I'm going to have really 34 plus 23, which is going to be 57. Now actually take a look here. What's the relationship between 57 and 19? 57 is 3 times 19. So the perimeter is also tripled, which is a cool relationship if you think about it. Since the perimeter is tripled, maybe we need 12 pieces? Well, if we're sold in 5-meter lengths, if we buy 12 pieces, that's going to cover 60 meters. If we buy 11 pieces, that would only cover 55 meters. So yeah, we will need 12 pieces, which is exactly triple of what we had before. So this is a cool, complex application, but really the key points for today are reviewing the distance formula, understanding how to find the perimeter, and what it means to be a convex and a concave polygon. Regular polygons have these same measurements, and if we want to think about what irregular means, it means that they have unequal sides. So review all these concepts, and as long as you understand the core concepts, you should be fine.